So it's my pleasure to introduce my co-organizer, joining us later in the week, Elina Robeva, who is going to speak on some of the CP decompositions, one of the big powerful tools in this tensor society. Okay, take it away.
Great, thanks so much, James, and thanks everyone for listening to me, even though I'm not there. So I'll talk about, okay, how do I change this? That's probably still, okay. Sorry. Oh. Okay, this should do. So tensor CP decomposition. And today I'll talk about the introduction and some examples of applications. All right, so for me, and by the way, if anybody has questions, please speak up. So I'm happy to answer any questions. So I don't know exactly what was said in the previous talk, but I will think about tensors as just multi-dimensional arrays of numbers. And I'm sure that some people will not be happy about this, but please bear with me. So my tensors T will be, for example, an N1 by N2 by up through ND array of numbers. And in what I'll be talking about, they will be in the real numbers or the complex numbers, and I'm sure that you can try to think about these notions also over other fields. And so today I'll talk about a way to decompose a tensor, which is called the tensor CP decomposition. So just a little bit of history. This decomposition was first suggested by Hitchcock in 1927, and then it was sort of forgotten, and it was again suggested by Cattell in 1944, and then it was again forgotten, and then in 1970 there were two papers in psychometrics that both simultaneously suggested it, which were Carroll and Chen, and also Harshman. And these guys called it the comp, and this one was called Parafak. And so I think that's where CP comes from, although it might also come from canonical polyadic decomposition, which is also CP. So there's two ways, and I'm not exactly sure which one it is, but in any case, it's called CP decomposition. And so, so this is sort of the history, and ever since then, people have been studying it quite a bit. But the idea is that you want to generalize the notion of matrix rank. And so let me just recall matrix rank. And so what is that? So we have a matrix M, and let's say that M has rank R. So let's say M is N1 by N2. And if it has rank R, then you can write it as a product, one way to define that, to impose that it has rank R is to write it as a product of A times B, where A is N1 by R and B is R by N2, right? So sort of, maybe if R is not very big, then it will look something like this. A times B. And R here is this. And so actually, another way to represent this is by saying that M is A1 transpose, okay, plus A2 transpose plus blah, 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 plus AR VR transpose. Where what are these A's and B's? Well, so the A's are the columns of A1 R, and the B's are the rows of B. So B1 transpose, like this. So, right, so the vectors A lie in R or C, let's say Cn1, and the vectors B lie in Cn2. Okay, so another way to say that a matrix has rank R is to say that it can be written as a sum of R rank 1 matrices, because each of these have rank 1. Okay, so, and this is the kind of notion that you can try to generalize to tensors, and you can say, okay, so let me just write this. So M is a sum of R rank 1 matrices. By the way, also if the writing is too small or too big, you can let me know. All right, and so for tensors, so a tensor T will have CP rank at most R if T can be written. So this is kind of high level. I'll define, I need more pages, as a sum of R rank 1 tensors. And so now I have to define what are rank 1 tensors. Okay. Okay, so now what is a rank 1 tensor? So, okay, so T, which will be, and here C and R don't really matter. It can be either C or R. Has rank R, rank 1, if T can be written as the following outer product. I'm not sure if you talked about this in the previous talk, but I'll define it. A1 tensor A2 tensor through AD, where, okay, so where AI lies in C to the Ni or R to the Ni. So it's a vector, and then what are the entries? So what is this? What does this mean? So the entries, so this T is a tensor, and its entry at position I1, I2, up through ID. So these are some indices, right? Because it's a multidimensional array, like a big cube of numbers. So what is one of these numbers? Well, it's just the product of the entries. So A1, I1, A2, I2, AD, ID. So similarly to how, rank 1 matrices are defined, here, so see, this is a rank 1 matrix, and its entries are, its ijth entry is the ith element of this vector times the jth element of this vector, and here now we have more than 2 vectors, and these are the entries. So this is a rank 1 tensor, and so now we can define the CP decomposition of a tensor. So a CP decomposition of a tensor T has the form T sum I from 1 to R. Okay, now this will be, so A1 I tensor A2 I. I just need to have one of these A's for each so I want to do a sum of rank ones, and so I need two indices, and they're in the superscript so that I can also have subscripts. So here A1I is in R, sorry, C, I mean, it could be R. In fact, we'll talk about this on Friday. A2I is in C and 2. ADI is in C and D. So this is a CP decomposition, and okay, so I actually have a question. I'm not sure if I'll be able to hear anyone, but can you easily see that every tensor has a CP decomposition for some R? Can you think about how to make one? If I give you any tensor.
Mari, you might have to unmute if you want to give it. If somebody gives an answer, it's Mari.
Yeah, should be.
Well, I can.
Sorry, is anyone saying something? I hear a little bit.
Could you repeat
Did
the
you say?
question, Mari?
Yes.
Yes,
What was the? I think I need to do the mic up front.
So, I don't know how to mute. Oh, maybe I do this.
You just turned her down.
Yeah, the trouble is to. Okay, so I don't know how to avoid a feedback loop on that computer. So I'll repeat the questions from here. Are you able to hear me, Elina?
Yeah.
Okay.
Yes.
So Elina asked us all a question, which was, can you see that every tensor would have a CP decomposition, just full stop? Is that correct?
Yes.
Okay.
Yes.
So that's the question to you all. Is it even possible that this might not exist sometimes? If that's
Well, that's my question.
right. So I'm repeating it for them because you can't see their faces, but they're all stunned. So
Okay.
I'm repeating the questions so they remember it. Now they're going to answer it because they're all brilliant at the same time. So what do you think, Mason?
Kind of the same as you were going off of where a tensor is an element of a tensor space. Isn't the tensor space, every element can be written as a linear combination of these rank 1 tensors?
So Mason is saying, I'll try to say what he's saying. He's saying that isn't every tensor going to be a linear combination of rank 1 tensors? That's what he's giving as an answer. Okay?
What? Yeah,
So-
but that's not a proof.
That's not a proof, right? Who wants to add to it?
Oh, okay, so over C, should be able to have a rank 1 that consists of a single 1 in any entry of the tensor and zeros everywhere else.
Yeah.
And then, so I should be able to take an arbitrary tensor and write it as a sum of rank 1s or writing it as a sum of all the rank 1s that have a 1 in some specific spot and zeros elsewhere, and scaling each of those rank 1s appropriately. Did I convey that reasonably well?
Yeah, that's exactly right. So if you take a tensor that just has one non-zero entry, that tensor has rank 1. So maybe I can write this here. So a tensor with one non-zero entry has rank 1 exercise. I mean, so just try to express it as an outer product like this of some vectors. So these vectors will be basically all standard basis vectors, and then you have a scaling, you can subsume it into one of the standard basis vectors. But that's exactly right. So then you can just express any tensor as a sum of its individual entries, which are going to be rank 1. And there you go. So then each tensor has rank at most the number of its entries, which is n1, n2 up to n times up to np. Right. So that's the maximal. I mean, anyways, there is an even more concise way. So you can even, let's say, take. How do you go back now? So, oh, here we go. So you can even take maybe the columns. I mean, that's all of the entries in the last dimension, all those vectors, and use those as some of the vectors in the rank 1. So, so you can show that you can express it as the sum of n1 times n2 up to nd minus 1 rank 1 entries, terms. So, yeah, so the answer is yes, every tensor has a CP decomposition, and the CP rank is the smallest r. So the CP rank is the smallest number r, such that this decomposition exists. Okay. So any questions so far?
I think we're
So
good.
we'll see. Oh, yeah?
We're good.
Good, okay. So on Friday, we'll be discussing the properties of CP composition, which are kind of all wild, but today we'll be talking about applications, or some motivation for why we should study this. And the applications that I have are kind of from machine learning, but also just some sciences. And we'll see how far we can get. So the first application is just the following. So I claim that joint distributions are tensors. Okay, so what I mean by this, so let's take x1, x2 up to xd be some random variables. Each of them, so the ith random variable takes values 1, 2 up through ni. So these are discrete random variables, and they each have some, probability distribution of taking each of these values. But the joint distribution of these random variables is an n1 by n2 up through nd tensor t, whose entries, entry I1, I2 up through ID, is the probability that x1 is I1, x2 is I2, up through xd is ID. Okay, so that's just the joint probability distribution of these d random variables. And that is a tensor, so that's already a tensor. And my question is, maybe we can try to answer this as well, is when are these variables independent? So can you see what happens with their joint distribution if the joint distribution tensor T, if they're independent?
Oh, that's not the
Put
good
a
one,
lot of them
right?
together.
Because it's, yeah.
I didn't quite hear.
I would want to product them together since they're independent, so the effect should be to just take the product of each individual probability.
Yeah, so, right, so this thing is a product, right? But what does it mean for the tensor?
It means it's a rank 1 tensor.
That's right. So the tensor will be rank 1. Sorry if somebody else said it earlier, I just can't hear everyone. Okay, so here we go. So they're independent if and only if they're joint, if this factors as the probability that x1 is I1 times the probability that x2 is I2 up through xd is ID. And if you remember the definition of a rank 1 tensor, it was exactly that each entry is the product of the entries of those vectors that it's the rank 1 tensor of. So here, if we consider these guys, they're vectors. These are the marginal distributions of the x's. So this p of x1 here means, let's say p of x I have a lot of i's, is a vector that says probability that xi is 1 times probability that xi is ni. Okay, so these are all vectors. Oh, all right, can you still hear me?
Yes.
Okay, great, I think yeah. So these are all vectors, so this tensor has rank 1. right? So that's what it means that they're independent. Now, any questions? Okay. So now, how about the following situation? It's called a hidden variable model. So suppose that there is some hidden variable z, which, so this picture is a picture of a graphical model, and it doesn't need to mean anything to you, but what it encodes is that these variables x1 through xd are independent given the value of z. So for every value of z equals to j, these guys are independent. And so what this means is that when you condition on z equals to j, their joint distribution, this is a tensor, but just conditional on z, is going to be rank 1. So it's going to factorize as the outer product of these conditional distributions of x1 given z equals to j times up to xd given z equals to j. And so if you take the full joint distribution, which was our original tensor t, then it's going to be, how do we do this? Well, we have to sum over all values of z, which exactly are, of the probability that z equals to that value, j times the distribution of the variables given z equals to j, which we know is this rank 1 tensor. And so this is just a scalar, right? So this is really a CP decomposition. So again, the scalar, it could be out here on its own, or you could just assume it into any of the vectors. So this means that T has rank at most R. I mean, so CP rank, but okay. I'm just going to call this rank. Of course, maybe there is an R, an even smaller R, for which you can write it like this, but all this means is that the rank is at most R. Okay, so maybe you're wondering, okay, you just made this up, like, is this even like a reasonable model to assume? So I have an example of this model that I can try to convey. So I'm just going to take d equals to 3, and I'm going to have x1, x2, x3, 3 variables, and so I'm going to say x1 is, I'll be looking at news articles in some newspaper or magazine, and x1 is the 10th word of a news article. X2 is the 20th word. I mean, these are just made up. You can say, choose a number. And X3 is the 40th word. And I'll explain to you why I'm not taking the first, second, and third word in a little bit. Okay, so I think there's, I don't know how many words there are in English, but let's say 5,000, 10,000. Like, I don't know how many. You guys know better.
Try 100,000.
100,000? Okay. Okay, maybe I'm. So, okay, 100,000. So that's really great. Yeah. Okay. And so now each of these words. So this is the same setup as before, right? So each of the x's has some distribution, and then what I'm trying to say is that each news article might have different topics. So there will be different topics. There could be, you know, sports or politics or science or anything like this. And let's say there are our topics. And given the topic, so given that
Elina, I guess something has changed in the way you write. We hear you very muffled.
Oh, really? Okay, maybe it's the internet. Can you hear me now?
Better now, yeah?
Okay, so given that the topic z equals to some j, let's say politics, then I claim, I want to assume that x1, x2, and x3 are independent. Okay, just like we had before. So just like before, I want to say that given the topic, my variables are independent. And what would be words from the document, and I wanted them to be kind of far away from each other, then they have some distribution. And so if you choose politics, then the distribution will, include more like political kind of terms. And if you choose sports, then it will have sports terms. But if the words are far enough apart, then I think it's kind of reasonable to assume that they're independent. And so they're joint distribution tensor conditional on z equals to j has rank 1, just like here, like this. And then if you sum over all the different topics, then the joint distribution tensor T will have rank at most R. Does that make sense? I guess I can't see anything, so maybe you're nodding, maybe not. And so now why is this interesting? Well, suppose that you have a lot of news articles and you kind of record this, you try to estimate this joint distribution tensor from the data. So you have an empirical estimate of this tensor, and of course it's very large. So what's going to happen is for each document that you see in your news article, you record, so in IJK, the IJK's entry, so maybe T like tilde IJK, this will be the estimate. You record the number of documents. So this will be number of documents or articles where 10th word is the word I, 20th word is the word J, and 40th word is K. Okay, and so this will be some kind of tensor of counts, and then you can divide the full tensor by the number of articles you have, and then you're going to have some tensor. And the claim is that this tensor will have a low rank. And so if you decompose the tensor, if you find its CP decomposition, then what you're going to find are going to be these, first of all, these probabilities, which will say for the different topics, what were the proportion of documents that had this topic. And then for each topic, you're going to have the distribution of the words in that topic. So you should ideally get a vector that says, okay, I mean, it's not going to be labeled. It's not going to say, oh, this is for politics, this is for sports, but maybe you can figure it out by yourself. And I didn't want 100,000 because it doesn't seem really big, but maybe if you restrict to some common words, then, okay, it will be smaller. Okay, so this was one example of topic modeling, and people have also kind of generalized this to more sophisticated models where, okay, each document might have, several different topics that it touches upon. So we can try to see what the model looks like there. But this is the simple case. Any questions? Okay, but can you still hear me?
Yes.
Okay, good, thanks. And is it still muffled, or can you hear me?
It's just fine.
It's just fine, okay, thank you. Okay, so another example I have is from chemometrics. And here I'm not an expert, so I might say something wrong. but let's see. So this is by Bro, last name. Okay. So here's the setup. So we have 5 samples, and in each sample, these are now chemical samples, they're not like statistical samples. And in each sample, we have, it's a mix of several chemicals with different proportions. And we don't know how many chemicals there are or what their proportions are. So we have 5 samples, and in each sample, we have a mix of several with different proportions. Okay, so sample I will have alpha I1 of chemical 1 up through alpha Ki of chemical K, and we don't know K or alpha. All right, and because we have 5 samples, we're going to try to somehow use all of this data in order to recover the unknown K and alpha. And so what you could do in chemistry, which I am a complete non-expert on, is you can find something called the excitation emission matrix. Create excitation. Oh. Emission matrix, or EEM. And what does it look like? So there are excitation wavelengths from 1 up through, so in this case they had 51, and emission wavelengths in this case up through 201. And so this is matrix MI. So we're going to have one such matrix for each sample, and now you can see where our tensor is going to be. So we're going to stack these 5 matrices, because there's 5 samples, together into a tensor and try to learn all the unknowns from there. But what is this matrix MI? So for each excitation wavelength, we measure, so for each excitation wavelength, you measure the fluorescence lifetime for each emission wavelength. So this means, so you excite with some excitation wavelength here, and then for each of the emission wavelengths, you see how long it emits from that wavelength. And that's what you record in that entry. So I'm going to write this. So measure the fluorescence lifetime for each emission wavelength. Okay, and so I have a picture, hopefully yes. This is one example of such a matrix where this is the excitation wavelengths here. This is the emission wavelengths, and this is what this EEM matrix looks like. Okay. So anyway, so you can do this, and you can stack the MI matrices into a 5, because we have 5 of them, by 201 by 51 tensor T. Okay, so this is an example where, okay, let me just say, in the previous example, we considered the empirical probability distribution. In this example, we consider a tensor that's just literally the data. So we just stack all of the data we have into a tensor. And in the next example, we're going to do something else. So in this example, we're doing this, and now how can we, so why does this tensor have low CP rank, and how is it going to help us? And so here's what happens. So let's consider chemical J. So for chemical J, we're going to record, let's consider this vector. So it's going to have one vector, so gamma J1 up through gamma J51. So there were 51 excitation wavelengths. And this measures how much it gets excited by each wavelength. By each excitation wavelength. Okay, so this is this gamma. So for each of these excitation wavelengths, you can, I mean, this is what gamma means. And then for each chemical, there's also the emission profile, beta J1 up through beta J201. So this is the emission profile. And it says, when it gets excited, how much it emits from each of the emission wavelengths. So it gets excited. Okay, so this means if it gets excited, it emits this much from the first wavelength after this much from the last wavelength. Okay, and then we also have the alphas, which were the proportions. Okay, so we have the alphas, the betas, and the gammas. Page. Okay, and so now, now I claim. So I'm going to look at an entry from my tensor T, which was this here. So T, A, B, C, that's an entry. So this is in sample A. So there were 5 samples. For emission wavelength B. And excitation wavelength C. Okay, so TABC will say, you know, how much in this sample, given emission wavelength B, how long it's emitting from wavelength C, and sorry, for excitation wavelength. For excitation wavelength C, how much it's emitting from wavelength B, for how long. And, well, this can be split into the sum over all the different chemicals. So for chemical J, there is alpha JA, and so alpha JA is the proportion of chemical J in my 8th sample. There's this much of it, and if you give it if you give it gamma JC of the excitation wavelength, then it will emit from the emission wavelength B for time beta JB, something like this. And so overall, my tensor T actually has this decomposition, which means that T itself has this CP decomposition, right? So alpha J, beta J, gamma J, something like this. So, so that's the main idea. And so let me show you a picture of sort of the outcome. So here's, so in that paper that I cited, they actually did this experiment, and they had, you know, this tensor. It's a sum of 3 rank 1s, and you can see that, you know, for each of them, you get the alpha, which is the concentration of each of the, I guess, 5 chemicals. Wouldn't there be 3 chemicals? Yeah, there's 3 chemicals, and oh yeah, these are the concentrations of this chemical in each of the 5 samples. Yeah, so these are the concentrations of chemical 1 in each of the 5 samples, and chemical 2 and chemical 3. And then these are the emission and excitation profiles that we have, the beta and the gamma. I may have switched beta and gamma. Anyways, so this shows you that this is an application of CP decomposition where you take the full data tensor and you decompose it. Okay, so any questions?
Yeah, really quick. So, sorry, just to reiterate, you're saying that you don't know the amounts beforehand, but in getting that decomposition, that tells you the amounts of the chemicals in the samples.
Yeah, exactly.
Okay.
So you don't know, you don't even know how many chemicals there are, but because the tensor turns out to be rank 3, then there are 3 chemicals. I mean, okay, they knew how many chemicals there were, and they recovered the correct concentrations of them when they did the decomposition. So the tensor encodes all of that. So the CP decomposition sort of really finds some hidden information that if you just gave it one of the matrices, so I think the main thing about CP decomposition is that usually it is unique. We'll talk about this on Friday. And if you just gave it one of those 5 matrices, the samples, then there's many different ways to decompose it. And that's not going to give you, that will not tell you uniquely the hidden information, but when you have a tensor, then it does. So that's why it's so nice. Any more questions? Okay, so how long do I have?
About 14, 15 minutes.
Oh, so I can actually take the full hour. Do you have a break afterwards, or what's your?
No, break.
No, 6 or 7 minutes.
Oh, 6 hours.
Okay.
Okay, so sorry, 6, 7 minutes.
Okay, good. It's okay because I can continue tomorrow. So I want to now define symmetric CP decomposition. Which, you know, is very similar to CP decomposition, except it is symmetric. So first of all, I'll have to talk about symmetric tensors. I'm not sure if you talked about them in the last talk, James. So T now is going to be n by n by n, d times. And by the way, D is called the order of the tensor. So tensor of order D, at least in my communities, I think in like physics they call it the rank of T, but we call rank something else. So for me, D will be the order of T. And then, so T is symmetric if when you take one entry, I1, I2, up to ID, and you permute it, so I1, I2, by D, so pi is a permutation, you write this like some, okay, permutation I don't remember how to write. I don't know, this is a sigma D permutation. On 1 through D. So if I permute the indices, then the entry remains the same. So for example, symmetric matrices, right? So for a matrix, Mij equals to Mji, that's what it means, it's symmetric here, D equals to 2, right? So a matrix is also a tensor. Or if you take D equals to 3, and so you have an n by n tensor, then Tijk is Tikj is Tjik is Tkji, and okay, now, okay, I don't have to write them, but there's one more. Okay, anyways, so now you can, of course, find the CP decomposition of a symmetric tensor. But because it's symmetric, you could also ask for its symmetric CP decomposition. And what is that? Well, you just, again, write it as a sum, I from 1 to r. And here I'm going to have some coefficient sometimes. So this is just a number of AI tensor itself. So this is D times. And you can actually write this shorthand notation on the I tensor power D. Okay, so this is exactly shorthand for saying I take the same tensor and I tensor it with itself D times. And a tensor of this form, so tensor A, which again is A to the power tensor power D, is a symmetric rank 1 tensor. Okay, so this lambda here, sometimes it matters if you're over R, because over the real numbers, maybe if D is even, you want to put a minus sign here. And if D is even, then you can't subsume this minus sign into the vector. If D is odd, then you don't really need lambda. Okay, and yeah, so for any symmetric tensor, you can find its CP decomposition or its symmetric CP decomposition. And some interesting things happen where we'll see that they might be, the ranks might be different. So, okay, I should define symmetric rank. So symmetric CP rank is the smallest R for which the decomposition exists. Okay, so I think maybe I'll stop here because tomorrow I'll talk about another example, and there we'll see a symmetric CP decomposition. But perhaps it's good to stop here and maybe take some questions if there's any. And if there's no questions, you can try to prove or disprove that if you take a symmetric tensor and you find its rank and its symmetric rank, if they're equal or not. Maybe start with matrices.
Did you get the question? If you didn't hear it, if you start with a symmetric matrix and you compute its symmetric rank, or you compute its regular, just straight old-fashioned row-reduced rank, do you expect them to be the same or different? So, if you can do that problem as a challenge problem, I think you're getting the basic ideas. Are there any questions?
Very nice paper if you could do that problem as a challenge problem.
Well, okay, true. But if you think about the problem, you think about what it requires you to do, I think you'll you'll start to understand what the questions are about.
You resolve the known conjecture.
We will pause here. We have another talk in about 10 minutes. And what we'll do, Elina, is you're still able to see the feed from the other link, is that correct? So we'll stop here. Thank you, Elina.
Which other, like,
There was an email sent out that has links to all the full room view. And so if you go to Echo 360, it's on the link that was sent out by Chris Liu yesterday at the end of the day.
Oh,
So,
yes.
yeah. So it says link here, and you click on the link there, I believe.
can you forward it because I can't
Yeah.
see it.
Well, I have to find it myself, and I'll send it to you in an email. Okay.
Thank you.
All right. Thanks. Bye.
Bye.